Welcome back to Blackboard AI, where we simplify complex algorithms. Today, we are tackling an intriguing problem called Make a Palindrome. It challenges us to transform an array into a palindrome using a very specific deletion operation. First, let us understand the problem. We are given an array O of size n and an integer k. Our goal is to determine if we can make this array a palindrome after performing any number of a specific operation. So, what is this operation? You select two indices, L and R, such that the subarray O at L to O at R has at least k elements. That is, R minus L plus 1 is greater than or equal to k. Then you find an index, I, within this subarray, where O at I is the kth smallest number in that specific subarray. If there are multiple candidates for I, you can pick any one. Finally, you delete O at I from the array, and the remaining parts concatenate. For example, if A equals bracket 1, 2, 2, 1, 3 bracket, L equals 1, R equals 5, and K equals 3. The elements are 1, 2, 2, 1, 3. Sorted, they are 1, 1, 2, 2, 3. The third smallest element is 2. So you could delete either at 2, which is 2, or at 3, also 2. The core question is, can we reach a state where the array is a palindrome, meaning it reads the same forwards and backward? This problem hinges on a crucial insight: which elements can we actually delete? The operation is tricky because it depends on the kth smallest in a subarray, not the whole array. However, consider this: any element whose value is strictly less than the kth smallest element in the original array can never be deleted. Let us formalize this. Take the original array, sort a copy of it, let us call it A-sorted. The kth smallest value in the original array is A-sorted at k minus 1, using zero-based indexing. Let us call this kth smallest val. Why can elements strictly less than kth smallest val not be deleted? Because if an element x has x is less than kth smallest val, it means there are at least k elements in the original array that are greater than or equal to kth smallest val. So, x can never be the kth smallest element in any subarray of size k or more, since there will always be k minus 1 or more elements smaller than or equal to x, and a sufficient number of larger elements to make x one of the k minus 1 smallest, never the kth smallest. Conversely, any element whose value is greater than or equal to kth smallest val can be deleted. Why? Because if such an element y exists, you can always choose the entire array as your subarray. L equals 0, R equals n minus 1. In this full array, y is definitely at least the kth smallest element. Thus, y is a valid candidate for deletion. So our strategy simplifies. Element's value is less than kth smallest val are undeletable. We must keep these if they are part of our palindrome. Element's value is greater than or equal to kth smallest val are deletable. We can get rid of these if they prevent forming a palindrome. With this crucial insight, we can employ a greedy two-pointer strategy. We want to form a palindrome by keeping as many undeletable elements as possible and strategically deleting deletable elements. Here is how it works. First, create a sorted copy of the original array, A. The element at index k, minus 1, 0 indexed, is our kth smallest val. Initialize pointers. Set L equals 0, start of the array, and R equals n minus 1, end of the array. Iterate and decide, loop while L is less than R. Case 1, A at L equals A at R. If the elements at both ends match, A at L equals A at R, perfect. They form a matching pair for the palindrome. We keep them both. Action, increment L and decrement R. Move inwards. Case 2, A at L does not equal A at R. Now we have a mismatch. To make it a palindrome, we must delete one or both of them. Subcase 2, both A at L and A at R are undeletable. Since they do not match, and we cannot delete either, it is impossible to form a palindrome. Action, output no and terminate. Subcase 2b, one is undeletable, the other is deletable. If A at L is less than kth smallest val, undeletable, and A at R is greater than or equal to kth smallest val, deletable, we must keep A at L. To resolve the mismatch, we delete A at R. Action decrement R. Symmetrically, if A at R is less than kth smallest val, and A at L is greater than or equal to kth smallest val, we delete A at L and increment L. Subcase 2c, both A at L and A at R are deletable. Since they do not match, we need to delete one. Because both are deletable, we have the flexibility. It does not matter which one we delete, we just need to advance one pointer to continue checking for a palindrome. For simplicity, let us say we delete A at L. Action increment L could also be decrement R. Final check. If the loop finishes, meaning L is greater than or equal to R, without hitting the no condition, it means we successfully resolved all mismatches or found matching pairs. Action output yes. Let us walk through an example to make this crystal clear. Suppose we have A equals bracket 1, 2, 2, 1, 3 bracket and K equals 3. First, find kth smallest val. Sorted as 1, 1, 2, 2, 3. For K equals 3, A sorted at K, minus 1 is A sorted at 2, which is 2. So kth smallest val equals 2. Elements less than 2, undeletable only 1. Elements greater than or equal to 2, deletable 2, 3. Initial state, A equals bracket 1, 2, 2, 1, 3 bracket. L equals 0, R equals 4. Iteration 1, A at 0 equals 1, A at 4 equals 3, they do not match. A at 0 equals 1 is less than kth smallest val, undeletable. A at 4 equals 3 is greater than or equal to kth smallest val, deletable. Action we must keep A at 0, delete A at 4, R becomes 3. Conceptual array 1, 2, 2, 1. Iteration 2, L equals 0, R equals 3. A at 0 equals 1, A at 3 equals 1, they match. Action keep both, L becomes 1, R becomes 2. Conceptual array 2, 2. Iteration 3, L equals 1, R equals 2. A at 1 equals 2, A at 2 equals 2, they match. Action keep both, L becomes 2, R becomes 1. Conceptual array, bracket bracket. Loop end, L equals 2, R equals 1. Now L is greater than or equal to R, so the loop terminates. Result, since we never hit the no condition, the output is yes. We could form a palindrome, in this case, 1, 2, 2, 1, from the original array by deleting the 3. The time complexity of this solution is dominated by the initial sorting step, which is O of n log n, where n is the size of the array. The two-pointer traversal takes O of n time, so overall it is very efficient. And there you have it. A seemingly complex deletion problem broken down into a clear strategy based on identifying deletable and undeletable elements, solved efficiently with a greedy two-pointer approach. If you found this explanation helpful, smash that like button, share it with your coding friends, and do not forget to subscribe to Blackboard AI for more in-depth algorithm tutorials. Thanks for watching and happy coding!